When we want to use analog filters in signal processing, we first have to design the filter, which gives us the filter transfer function h of s. The next step then is the filter realization, or in other words, how the filter can be implemented using physical components. Let's assume that we have designed this third-order filter with coefficients b0, b1, b2, b3, and a1, a2, and a3. Provided that all coefficients b and a are real-valued, this filter can be implemented using three basic elements or components. The first component is the inverting amplifier, for which we know that the output signal y is equal to the input signal x scaled with minus rf divided by ri. Or expressed in the s domain after applying the Laplace transform, y of s is equal to minus rf divided by ri x of s. In block diagrams, such amplifiers are usually visualized with such a triangle, with amplification factor k, which in this case is equal to minus rf divided by ri. An alternative way to mark the transition between the input signal x to the output signal y is by simply writing the amplification factor k above the line connecting the two signals. The second standard component that we need to realize our filter h of s is the operational amplifier summer, which can be understood as a generalization of the inverting amplifier. The output y of t is equal to the weighted sum of the input signals x1 till xn. In block diagram drawings, this can be symbolized by a big triangle with amplification factors k1, k2 up until kn, where km is equal to minus rf over rm, or by these summation symbols with the same factors k1, k2 up until kn. And the third component is the integrator circuit. If we assume that the output signal y was 0 at time equals 0, then y of t is equal to minus 1 divided by rc times the integral between 0 and t of the input signal x. In block diagram drawings, this is symbolized by this integrator block with amplification factor k, which here is equal to minus 1 divided by rc. When applying the Laplace transform, the output in the s domain y of s is equal to minus 1 divided by rc times 1 over s times x of s. Hence, the integrator can also be symbolized by a block containing 1 divided by s and the same amplification factor k. Now we will see how these three basic elements, this is the inverting amplifier, the summer, and the integrator, can be used to realize a simple analog filter. For this, let's go back to the example of a third-order analog filter with transfer function h of s. Because the integrator allows us to implement 1 divided by s, but not s, we will rewrite h of s so that it contains polynomials in 1 divided by s, rather than polynomials of s, by taking out the factor s to the power of 3, which can then be cancelled out. The next step then is to separate the numerator from the denominator polynomial, such that we get the transfer functions h1 and h2, such that h is equal to h1 times h2. This implies that our filter can be implemented or realized as a serial or cascade coupling of h1 and h2. We will start with the realization of h1 of s, such that ws is equal to b0 plus b1 divided by s, plus b2 divided by s squared, plus b3 divided by s to the power of 3, times x of s, which can be expressed as a block diagram of this form containing 3 integrators and 3 summers. To realize the transfer function h2 of s, we have to use feedback coupling. To see this, let's first rewrite the equation y of s equals h2 of s times w of s by multiplying both sides with the denominator. Then y of s is equal to w of s minus the weighted sum of the first 3 integrals of y, which can be realized by this block diagram, again containing 3 integrators and 3 summers. Combining these two parts yields the realization of our filter h of s. This particular realization is called the first direct form, or direct form 1. An equivalent realization of our filter can be obtained by changing the order of h1 and h2 of s. When doing so, we see that the same signal is integrated in both chains of integrators. So, an easy way to save resources, in this case here this means saving the amount of integrators that are needed, is to combine those two integrator chains, so that we only need 3 integrators in total. This realization is often called the direct form 2 or the second direct form. Let's have a look at the following example, where we want to realize the filter h of s equals 2s plus 5 divided by s squared plus 4s plus 10, using only inverting amplifiers, summers, and integrators. The realization of this filter in direct form 2 is given by this block diagram, where we can easily combine two of the summers. Slightly reorganizing the blocks yields this block diagram. Since we want to implement this filter using only inverting amplifier, summer, and integrator circuits, which all introduce negative signs, we have to keep track on how often the sign of a signal is inverted. For this, we change the symbols in our block diagram. The summers are substituted by triangles with the negative amplification factors, and the integrators are substituted by a triangle together with the small rectangle and amplification factor -1. To check if the output signal is calculated correctly and with the correct sign, we will mark all signals with a positive sign in green and all signals with an inverted sign in red. We assume that our input signal x of s has a positive sign. Due to the negative amplification factors of the summer, the output will have a flipped sign. After integrating the signal the first time, the sign is flipped again, which also affects the sign of the first feedback loop. In this case here, this would correspond to a positive feedback loop, because a closed loop includes two general inverting amplifiers. This is undesirable. Instead, what we want to achieve is a negative feedback loop. Hence, another inverting amplifier with gain -1 has to be introduced to flip the sign. The output of the second integrator then has a flipped sign again, such that the output of the second summer has a positive sign, and there is no need to introduce another inverting amplifier to correct the sign of the output signal y. The output of the second integrator is also fed back to the first summer of the system, here with a negative sign. Since we want to achieve a negative feedback loop, we don't need to introduce another inverting amplifier. We want to ensure that the signal w of s is equal to plus x of s minus 4 times 1 over s times w of s minus 10 divided by s squared times w of s. This can be rewritten as minus w of s, which is the output of the first summer, equal to minus x of s plus 4 divided by s times w of s plus 10 over s squared times w of s. Hence, the input signal x of s should be multiplied with the amplification factor -1. This is indeed the case. Next, the first integral of w of s, this is 1 divided by s times w, should be multiplied with the amplification factor +4. This is achieved by choosing -4 as an amplification factor of the summer, but using the signal with a flipped sign, here marked in red. The same is true for the last term, namely 10 times the second integral of w, namely 1 divided by s squared times w of s, for which we use the amplification factor -10. Again, the negative sign of -10 is cancelled out by the fact that we feed back the signal with a negative sign. The last signal for which we need to check the sign is the output of the first integrator, which is fed into the second summer. Since the sign of the output signal is flipped again by the second summer, we want the input signals to the second summer to have negative signs. To flip the sign, we need to add another inverting amplifier with gain -1. The first summer can now be implemented using an inverting amplifier, two 100 kilo-ohm resistors, one 10 kilo-ohm resistor, and one 25 kilo-ohm resistor. The second summer is implemented by an operational amplifier and three resistors with resistances 100 kilo-ohm, 50 kilo-ohm, and 20 kilo-ohm. Whereas the two integrators are implemented using an operational amplifier, a capacitor with capacitance 10 microfarad, and a resistor with resistance 10 kilo-ohms. And as a last step, the two inverting amplifiers with gain 1 are implemented with one operational amplifier and two resistors of value 100 kilo-ohms each. In this example, we have seen how to implement a simple second-order filter in the direct form number 2. In principle, this method can be used to realize and implement any proper filter with real coefficients. However, as we have seen in this example, even the implementation of a simple second-order filter becomes relatively complex and cumbersome. Also, with this method, we need in total 6 operational amplifiers, 2 capacitors and 13 resistors. Instead, it would be useful to know other realization methods that lead to less complex implementations and require less components. To understand how alternative methods work, we will go back to this general nth-order transfer function h of s, which we can also write in the pole zero form with amplification factor k, zeros z, and poles p. Instead of implementing or realizing the entire system at once, it is first broken up in small subsystems. For this, we have in general 2 options. The first option is a cascade or serial coupling of m subsystems, where each subsystem should contain at most 2 poles and 2 zeros of the original system. Which poles and zeros are chosen to be in which subsystem can be chosen relatively freely, as long as complex conjugate pole and zero pairs are part of the same subsystem. This is to ensure that all coefficients of the subsystems are real valued. Such a second-order subsystem is also sometimes called a second-order section, or in short, SOS. The overall transfer function h of s is then the product of the individual transfer functions h1, h2 up until hm. Another alternative is to use parallel coupling of m subsystems, where the overall transfer function h of s is then the sum of the transfer functions h1, h2 up until hm. The transfer functions of the subsystems in parallel coupling can be obtained by calculating partial fractions. Keep in mind that the transfer function of a subsystem in parallel coupling, for example h1, is in general not the same as the transfer function in serial coupling. The individual subsystems can then be implemented using known first and second order standard filters, as for example a first order low pass filter, a first order high pass filter, or for example this second order band pass filter. Another option to implement second order systems is to use the cell and key realization, which includes 1 operational amplifier and 4 complex impedances Z1, Z2, Z3 and Z4. By choosing those impedances appropriately, this filter can be converted into a second order low pass, high pass, band pass or band stop filter. A second order low pass filter with a complex conjugate pole pair can for example be implemented using 2 resistors and 2 capacitors.